Thank you.
All right, and since he couldn't pronounce it, it must be new technology that everybody wants to learn about, so that's great. So I'm Mike Heinowski, KD2EAT, from Ithaca, New York. I'm the advisor for the Amateur Radio Club at Cornell University. I'm a baby among this group. I've only been a licensed ham since 2012. And I'm probably still the youngest ham, or nearly the youngest ham in our local ham club. Not by years of license, but by chronological age. So I'm always doing the crazy stuff back home. So today I'm going to talk a little bit about some of the newer stuff that we've been doing with trackers and basically using radiosondes as trackers. So a growing hobby that's picked up lately is collecting radiosondes, and two very common ones in the U.S. are the DFM 17 and the RS41. These things are just literally falling from the sky. And you know, when you think about what you need for a high altitude balloon tracker, what you need is a device that has a GPS and a microcontroller and a transmitter. And when you think about what a radiosonde needs, it needs a GPS and a microcontroller and a transmitter. And so there's a lot of commonality there. So basically, free trackers fall from the sky, and they're launched from hundreds. I don't know if I have the right number there, but hundreds of them are launched every day. There are people who collect them and trade them and give them away and sell them on YouTube or on YouTube, yeah, eBay. So they're widely available. So I pick them up a couple times a year when they fall in my area from the Buffalo National Weather Service. I'm about 150 miles away from Buffalo, but in the high wind part of the year, they drop in my area occasionally, and I get enough that I can use them as trackers and give them away occasionally. So there's pictures of what I just waved around for a little better imagery. Normally these sensor stalks, we don't use them for ham tracking, and in fact these sensors, generally there's a lot of calibration data stored in the microcontroller about those sensors that when we reflash the software that runs on these things, we lose all that calibration. So we just take them off. It's just a useless weight. So we remove those. Yes?
I heard that they use that as part of the antenna.
I have heard that this is used as a counterpoise on the DFM 17, and that some people, you know, do something about a counterpoise, whether they leave that or just put a wire counterpoise on there. I have not done that. I don't have extensive experience launching the DFM 17s. I've launched a couple and I haven't had issues with it. So I just take it off, but it's probably not a bad idea to put it on as a counterpoise. Somebody with more energy or somebody with a good spectrum analyzer might want to test that sometime.
That's just how they're set up.
So I talked about reflashing software. So there's software called RS41, and there's a bunch of varieties of it. It started out with RS41 HUP. I don't remember what HUP stands for. But Mikhail and this, talk about butchering last names, Nusianin from Europe took RS41 HUP and basically created RS41 the next generation software, and he added some different modulation schemes to it and basically restructured the code and made it a little more accessible to work with. And so when you take and by the name of the software, you can tell that it was originally designed to run on the RS41. So it'll do APRS at 1200 baud, but note that 70 centimeter APRS. It'll do Horus binary, which I'll be talking about quite a bit. CW, it does a PIP mode, which is just sort of a beep. And with the RS41, there's actually a expansion port on here that does I2C. And if you put an SI5351 module, like Bill passed around earlier, it'll do additional modulation types. It'll do JT95, JT65, JT9, all the ones listed there. So it's pretty cool software. So basically you can flash that down onto the microcontroller. So here's what the inside of one of these looks like. And I actually took the antenna off and I put an SMA adapter on it so I could do some testing at home. And to reflash it, you can go on Amazon and buy a $15 ST-Link dongle. And basically you put the correct wires into this. I just do it the old-fashioned way. I just plug these in there and stick that in your computer and run the right software, and you can download new firmware onto this tracker. And in fact, I'll be doing that with Andrew later this afternoon because he inherited a free balloon And he's got an RS41, so he said, hey, I got an RS41, that means I got a free tracker and a free balloon, might as well throw it in the air tomorrow. So we're going to reprogram one of his RS41s and put it in the air tomorrow. So, we noticed that the RS41 and the DFM17 are very, very similar pieces of hardware. And we said, what if we could take that software that we run on RS41s and put it on the DFM17 as well? So Michael and I took a look at that, and the answer is we could port it, and we did. And recently there's a newer version of the RS41 being flown in Europe, and basically due to chip obsolescence. These were manufactured at a time when some of the chips on here are just now unobtainium. So they did a hardware refresh. So the RS41NG software won't work on the new RS41s, but right now those are predominantly in Europe. So, but I'm looking at porting that as well. A guy from Germany sent me an RS41, the newer version. I got the hardware sitting on my desk at home, and it looks to be kind of a large process, and I'll show you why. This is sort of a comparison chart of the components on these things, and you'll notice as you go down the RS41 column and the DFM column, a lot of similarities. They're both using the STM32F100 series microprocessor. Basically, the last two digits are the form factor, 48 pin versus 64 pin. So it's the same processor, it's just different pin out. So some of the work of the port was just figuring out how they map the pins when they on the DFM17 versus the RS41. Same clock speed, same flash, different U-Blocks module, but we actually didn't have to make any code changes for that. It's backward compatible. The real big difference was the SI4032 on the RS41 versus the better, newer SI4063 that's on the DFM17. And another interesting feature that some people have asked about is, notice the frequency range, the bottom end of it here. Here is why you can't run 2 meter APRS on an RS41. The chip doesn't go that low. SI4063, the chip does go that low, but there are still issues, and I'll talk about that. And the other difference is that the RS41 uses inexpensive AA batteries, and the DFM17 uses princely some price CR123 batteries. The ultimate lithiums of those are expensive. Ultimate lithiums are expensive anyway, but the CR123s are painful. So the newer RS41, you'll notice the processor type, STM32L412R. It's a different processor. Same family, but the low level called HAL, hardware abstraction level code, is different. And so basically these two trackers, we could use the same hardware abstraction layer software to use them. This one's going to need a whole different HAL layer. I think. We may be able to get away with it, I'm not sure. So one thing I need to test is, can I use the old hardware abstraction layer on the new, and did they keep enough backward compatibility between processor models that I can get away with it? If not, it's basically replacing the whole hardware abstraction layer of the software with a newer version, which might mean a rewrite, because it wouldn't be a bad idea to put a newer, more modern HAL layer in these as well. So it turns into a big project potentially. It's either going to be really easy or really hard. I don't know which yet. But you'll see it also runs faster. It's got more flash, RAM and flash. Again, a newer U-Blocks module. Same old ancient SI4032 though. So that's the differences. So I'll be looking at this one in the coming year. But the one nice thing is that the DFM17 will now run RS41NG, which is kind of nice. But, he said, there are issues with the DFM17. It's because it's cheaper hardware. Basically, clock drift is a big issue on the DFM17. Whereas on the RS41, the microprocessor runs off a crystal, but they have a TCXO, a temperature-controlled oscillator, running both the GPS and sharing it. I'd never seen that actually. The TCXO output gets forked off, and one goes into the GPS and one goes into the transmitter chip, which is pretty slick. So they got away with one TCXO chip. They're a little expensive. And the processor doesn't need to be as accurate, but the processor is still running with a crystal. Crystals will drift with temperature, but not as bad as an internal RC oscillator, which is what the DFM17 runs. there are, it's just got an internal RC oscillator. Those things are horrible. They, from unit to unit, the clock speed will be very different in otherwise identical conditions, and they'll swing terribly with temperature. So DFM 17 has some issues there. The GPS has a crystal and the transmitter has a crystal, but again, notice crystal versus TCXO, so the transmission frequency drifts. So there's sort of two issues here. The internal MCU drifting, that impacts APRS, because with APRS you have a 1200 baud signal, which is being modulated each 1200 times a second. You're making a tone. Each of those tones actually needs a couple of clock cycles or ticks to establish sort of the sine wave of the signal. And when that varies, your 1200 baud can drift anywhere down to 1100 baud to 1300 baud, and that can cause problems decoding. And in fact, it was interesting because just by dint of luck, when I started testing DFM 17s, very nice guy on the internet sent me a dozen of them. He collects them. He goes out chasing radiosondes, and he said, "Oh, you need some DFM 17s for testing?" And he sent me a box of 12. So I grabbed the first one out of the box, started using it. It had the worst crystal, so I couldn't get DFM or couldn't get APRS to decode on that one. And I said, "Is this bad?" So I put it aside, grabbed another one out of the box. APRS decoded great. And so I got 5 out of the box, and I ran them side by side, and one of them just wouldn't decode. It was perfectly functional, but the clocks were just so far off, it wouldn't decode APRS unless I used Direwolf. Direwolf is great. It'll decode anything. But my radios wouldn't decode it at all.
Question?
Yeah.
On the RS41, does the GPS discipline the TCXO?
No. Let me pause. I'm not sure, and I'll tell you why in a minute. It's actually, I think, the next foil. So one of the things we did, here's frequency drift. So here's Horus binary on an RS41. And, well, let's see, which is which? I think I have them side by side later. But here's the frequency drift, and you notice at the top here we're at like 432.648, and at the bottom we're at 432.646. That's 2 kilohertz difference in frequency while it's flying, which is pretty nasty to decode when you have something drifting that much in frequency. And you can see that the temperature drop is kind of pretty heavily related. It came up and the frequency went up, it went down, the frequency went down. So yeah, this was a 2.7 actually, 2.7K frequency drift on a protocol that's about 300 hertz wide. Or I think it's wider than that, but it's a pretty narrow protocol. So, but compare that to an RS41 frequency drift, and it's varying, it varies too, but here we had like a 300 hertz frequency drift through a temperature swing. This temperature swing wasn't as dramatic as the other one, but still 300 hertz versus 2.7 kilohertz. Quite a big difference that TCXO makes.
Do the radiosonde tracker people have trouble with that drift on the DM17?
I believe they do play some tricks with it. I don't know what they do, but I think they play some tricks on the DFM17 to deal with that,
Well, they put
to
it
compensate in the software. And in fact, that's the thing I'm thinking about is, I could just run a bunch of flights at DFM17, bust open that box of a dozen and fly them and collect some data. And I could literally just make a table that says at this temperature adjusted by this percent, or come up with a formula to tweak it, to see if I can tweak the frequency to stay in tune.
Have you tried just opening the receiver bandwidth to see if while it's drifting it still stays fully inside the modulation window?
I have not, because there's other issues there that I'll talk about when you're running multiple at once. When you're running one, it's really not that big a deal. You can tell the software, Horus Demod Lib, which I'll talk about, to listen on a wider, like 8 kilohertz, and it's probably not an issue. But there are problems with that as well. So the RS41's not bad. So clock drift is also an issue. I touched on that. One of my DFM17s was not decoding. Took me a long time to figure out why. And it turned out that clock in that particular one was running about 5% slower than all the others. Turns out you've got this GPS sitting on the tracker, and you've heard of GPS disciplined clock sources. And I said, hey, can we do that? And the answer is yes. So the GPS generates a 1 hertz, exactly 1 hertz time pulse, and there was a pin attached to a GPIO that I could read. And so basically from the software I can tell exactly how long 1 second is, and I can compare what the microcontroller thought was a second to what is really a second, come up with a percentage, and then there is a function in the microcontroller to tweak that internal oscillator up in steps of like 3% up or down. And so what I did is I added to the main loop. Every time we're sort of looping around, compare, and if I'm drifting off the MCU clock, apply that drifting factor. Fixed APRS on the DFM7, on my bad DFM17 just fine. And that'll actually run during flight. So if we have temperature drift in flight, it'll adjust it. So that's kind of nice. It's in 3% chunks, but it's better than nothing. So that helped a bunch. But as we talked about for the frequency, what I'm thinking about doing is seeing if I can come up with a formula based on temperature drift and see if I can look at the internal temperature of the board versus what it was, and see if I can come up with a sensible solution to just tweak the desired frequency to kind of keep it in line. And we'll see how that works, or if it works. So I think I talked about that stuff. All right, so the next thing is I pointed to the DFM17 and noted that the transmitter chip on there, the SI4063, will go down low enough that you can cover 144 megahertz. So you could do 2 meter APRS with the DFM17 conceivably. You just need to swap out the antenna or transmit on a compromised antenna, which probably wouldn't work so well. We're only talking about 50 milliwatts here anyway. But it mostly fixes our APRS, but bandpass filters could be a problem because the bandpass filters on that antenna are tuned for 70 centimeters. So if you're making 2 meters, it's going to attenuate your outbound signal. So you might want to muck around with the filters. But I said, look, I got a spectrum analyzer and not enough time on my hands, let me play. So I can't wait till I can retire. It's just this whole money thing I'm hooked on. So 70 centimeter out of the DFM17. Look at that, nice, clean, boom. That's Horus modulation, I think. I just caught it while it was squawking. Nice and clean. And then I just literally, in the Horus config file, changed it to APRS frequency. And what's really interesting is here's the frequency of interest, 144.390. The third harmonic is at 430 megahertz. It's in the 70 centimeter band. You'll notice the third harmonic has more output power than the primary frequency because of the filters. But spattering crap all over the bands. So again, it's 50 milliwatts or something, but you are airborne. But if you want to be a good ham, you want your signals to look like that one on the end. You don't want your signals to look like that.
Reprogrammed through the forum to the 144.39, and if you tune in the APRS on 433.168, you can receive it. I thought I could double bank things.
Yeah, so this is, the filters are an issue. And, the enterprising ham may say, well, I could change the output filter on the DFM17. And I'm an enterprising ham, but the filter, I believe, is 0201 surface mount parts. I can work with 0402 a little bit, and I'm pretty good with surface mount stuff, and 0402 is my limit, and I don't like it. 0603 I'll do all day. 0201, I mean, they make grains of sand look big. So yeah, no thanks. I'll do something else. I got better ways to torture myself. So anyway, that's the situation with that.
Could you strip those small parts off and then build
something out for it? You might. That would be pretty simple, just to straight line it, and then as I did, you might even just stick an SMA filter or SMA connector on there because the board has SMA pads on it. Tear the antenna off, put an SMA, and then get an inline 2 meter. That's conceivable. And since you're using this for halves, not for picos, a couple grams more weight, who cares?
Yeah.
So, yeah, it's not a bad idea. The other thing I forgot to mention with the DFMs that is somewhat of a barrier to entry is the connector to program it. Whereas the RS41 has this nice big, they're 2mm pitch. They're not the usual 2.54mm standard jumpers. So I actually bought little adapter jumpers. This is normal 0.1 inch, 2.54mm on this end, and 2mm on that end. And they fit nice and snug in here, and it works really well. You can actually get away with standard jumpers. They don't fit great, but they'll fit long enough to program it. This one, they do not have jumpers, they just have the pads on the board. And you can buy a little, just 10-pin thing to solder on here. It's fussy, and again, I'm pretty good with surface mount, and it's fussy. And at least the jumpers that I bought, they have plastic on them, and the plastic is not as heat resistant as I would like it to be. So basically 1 out of 3 times I melt the connector, throw it away, and try again. But once you get that connector on there, I actually programmed the DFM 17's with a real ST link, which has got a little cable, and you can literally just pop it on like that, nice and easy, and that's how I program this guy. So the fight is just getting the connector soldered onto the board, but after that, programming's a dream for that. All right, so I mentioned Horus binary. So crackpots like me like to try different stuff. And Project Horus in Australia, they do some amazing work. I love everything they've done. I'm running most of it at this point, or a bunch of it. They came up with a new protocol for tracking called Horus binary. It's a 100 baud 4FSK protocol that has forward error correction built in. Normally, we transmit it with like 25 milliwatts. And basically, you can decode this as far as the eye can see. So as far as if the balloon is at altitude, you know, we've launched these in Buffalo, and I've decoded it from my house 150 miles from there, no problem at all. It's a great protocol. It's much easier to decode than APRS, so I really like it. They designed in the protocol, the telemetry is really optimized for balloons, so you're not wedging, you know, balloon telemetry into APRS. You don't get grumpy people in the neighborhood who don't like seeing balloons beaconing once a minute while they're in the air, complaining about how you're going to destroy the APRS network and melt down servers everywhere. So, you know, this is just off doing its own thing. It's out of people's way, and it's actually much more efficient and decodable than APRS. Problem is, of course, it's not the APRS network. You don't have digipeaters and iGates running all over the place. You're more self-sufficient if you want to do this. So the advantage, the link budget, about 16 to 20 dB better performance over APRS. So it can get a lot farther out there, a lot weaker signal, and still be decoded just fine. It's receivable basically to the horizon, and you need to run some software to receive it, but a cheap SDR and a quarter wave monopole on a Raspberry Pi, and you've got a receive station that'll receive it just fine. My receive station looks a lot more complicated than it has to be, but I'm actually set up to receive 2 different protocols. But this is my entire mobile receive station right here. It's got a Raspberry Pi, 2 SDRs. I even have a little OLED display. It's running off a USB power brick. I even have a preamp on here and a splitter because I'm also going to be receiving WeNet during my flight, which is a video or image protocol. It's like SSDV but on steroids. So that's my mobile receive station. That'll be in my car tomorrow. And I'll have one in my RV as well, just for redundancy. So it sends packets up to about every 4 seconds. So instead of once a minute, praying that the next packet comes in and is decoded, you get one every 4 seconds. So you get a lot of live updates. Great for near ground final spots. You know, I've been near the landing zone waiting for that last packet to come in, and it comes in at 5,000 feet. And then a minute later, it's just above the ground and it's behind a tree or something with APRS, and I don't receive the final packet. And so you end up having a square mile to walk around with your HT, waiting until you hear the squawk and decoding it on your D72 or something. Not a problem, because I'll admit, I run low power APRS. 100 milliwatts is big time for me. I know you guys like to run like 100 watts of APRS on your payloads because you can't lose them because you're being, you know, you've got people who are reliant on it. I'm a little less paranoid about it, so it's more of a hunt and less of more of a game for me. But it's great for near ground spots because now instead of once a minute, I got, you know, every 4 seconds, if you could do the division, I can't. A lot more packets coming in. And the reception statistics are all uploaded to Grafana. If you use Amateur Sound Hub, you've probably hit the plots button and seen all that data. In fact, that previous data I showed you was off Grafana. And you know, you've got more granularity on that data again. It looks pretty cool. So challenges with Horus binary. Yeah, I love it, but it's got challenges. There's few receive stations, usually just me. The last several flights I've done has been a receive station at my house and a receive station in my car. And 3 out of the last 4 flights I did, I watched the payload land because I had great telemetry and great predictions. So you don't need many. Each transmitter needs a unique frequency unless you're time slotting. I've never actually done time slotting with Horus because I like the frequency of the packets coming in, and there's not many people using it in my area. So I can just blast out those transmissions. But it is narrow bandwidth, so you can slot multiple together and use one receiver to receive multiple. And in fact, I just contributed back to Project Horus the script that'll do 8 at once. So you tune your SDR to one frequency and you can receive up to 8 Horus trackers. And we're going to be exercising that tomorrow. So receiving Horus binary, you have sort of 2 choices right now. There's Horus GUI, which gives you a nice graphical display, or Horus DModLib, which is really just a set of scripts that run in Linux. I've been a Unix programmer for 40 years, so I'm very comfortable in Linux. And you know, in my opinion, ham radio 50 years ago was tubes and wires. Now ham radio is software. So kicking and screaming, we gotta get everybody up to using software for this stuff. So Horus GUI, I have a link there in the presentation, which will be on the web at some point. And it's supported on Mac OS, Windows, and Linux. Gives a graphical view of the signal. You can see the four frequencies, and you can watch the data come in, and you can show the decoded telemetry, and it'll uplink that to amateur.soundhub. And by the way, if I slip and say HabHub, just translate that to SoundHub. So here's an example screen out of Horus GUI. I just took this right off the website, but you can see you know, the 4 frequencies. You can see signal to noise ratio, how strong things are. Here is the string of decoded data from the last packet, or string of encoded data, and then how it decodes, and then it blasts that out into, you know, call sign, lat long, bearing, all that kind of stuff. And here is some output of Horus DModLib, which runs under the hood, uploading that to SoundHub. And then over here, I think there's some radio buttons to control how it does things.
Does that feed to Chase Mapper?
Yes. So that works with Chase Mapper as well.
Can you repeat the question?
Oh, sorry. Yes, the question was, does Horus GUI upload to Chase or work with Chase Mapper? And the answer is yes, it does. So Horus DModLib is a set of Python scripts and C programs that decode the telemetry. Horus GUI uses Horus DModLib, and you run the scripts on the command line. That's how I've been doing it on my Raspberry Pi. And so I have my Raspberry Pi, as you saw, just running headless. And when it boots up, it launches Horus DModLib, and off we go. Earlier, because Max had his tracker beaconing, I opened up a shell window and tailed the log file. If you're a Linux person, you'll understand what that means. Tailed the log file of my Horus DModLib, and here's the packets from his tracker coming in. He's got the tracker set up outside, and it was being received by my receive station. And so that's what it looks like. So you can see the received encoded data, decoded data, and then it tells you, hey, I uploaded one to SoundHub. So over and over again. So that's what that looks like. And it's still working. You see it scrolling. So we're still getting packets from Max's tracker. So it's still working, apparently. Get back to the presentation. Yay! Now, can I start from the current slide? Yes. So that's what that looks like. So again, it's a Raspberry Pi, an SDR, an antenna, power source, and you're good to go. Oh, and I cut and pasted that into the presentation right there. So that's what that looks like. Configuring Horus DModLib, again, it's Linux. It's a script. You're going to edit a file. You're going to put a few things in there. So there's a user config file where you set a call sign and your station location. So if like you have a home QTH, you could just put your coordinates in there. If you don't, if you're mobile, don't worry about it. And customize the receiver script you want. So again, if you just have one tracker in the air, you probably want to start with start RTL SDR.sh. It's just programmed for one tracker. You put in the frequency, and it has a very wide bandwidth that it receives with. And then, so that'll work really well with the DFM 17's, for example. But then there's one that'll do if you're doing two trackers, and I ran this one a lot. So I run two trackers, 10 kilohertz apart, and basically one receive from the SDR. It's 48 kilohertz wide, and I'm looking at 10 kilohertz slice of it, and I'm pulling out two Horus transmissions out of that slice. And then Mark wrote a triple, and then a couple weeks ago I wrote an 8. And we're going to try the 8 tomorrow. So be mindful of the spacing set in the config files. Max bandwidth for all trackers combined is about 48 kilohertz. So if you tweak those scripts, your SDR is, it's opening up a receive on the SDR that's 48 kilohertz wide. So if you set a frequency outside of that, you're just not going to hear it. So here is an example that I sort of made tabular so it's a little easier to understand. In this script, there is a RX freq, which is basically your center frequency. So I set that really weird center frequency, but the point is I want to have trackers at 5 kilohertz spacing between 432.605 and 432.640 at 5 kilohertz spacing. So the middle of that range happens to be 432.625, whatever. All right. Then there are 8 constants that you don't have to tweak that I put in the file. And I'll start it near the middle. So the center frequency is sort of here. Near the middle, minus 2500. If you take 2500 out of here, you're going to be at 432.620, which is one of the frequencies we want. If you take 7500, you're going to be at, and this is a minus, by the way. If you take 7500 away, you're going to be at 615, 432.610, 432.605. And then here we get additive. We add 2500 to this, 432.630, I think, if I'm doing it right, or 625. 625, 30, 35, 40. So this is all this is hard-coded. So all you really have to do if you want this range, leave it alone. If you want to move this range, just pick a different center frequency. So that's just edited in the file. And off you go. So that's how the 8 tracker script is set up. As noted previously, the DFM 17s have really bad frequency drift. So if you're 5 kilohertz apart and you're drifting 2700 up or down, you're going to be slamming into each other. So you really can't do that with the DFM 17s. But the RS41 should be fine. So you can space them very widely apart. So dual is fine. So for example, in the dual, you might say, did I do this? I don't know which yeah, I did. So in the dual, you could say, well, here's my center frequency, or my and this one's the beginning frequency, 432.600, and then add 5,000 for 432.605, and add 15,000 for 432.615. So you've spaced them out 10 kilohertz apart. And here also note the RX bandwidth, which is 5 kilohertz, and the other scripts is 8 kilohertz to give you a little more wiggle room with the DFM 17. So if you want to play with it, that's a way to do it. Again, don't mess with the bandwidth and don't put things closer than 5 kilohertz apart, and you're probably okay. So all of this integrates with Horus Sound Hub and Chase Mapper. So Horus DeModelLive and GUI will upload telemetry to amateur.soundhub if you have internet connectivity. They also use what's called payload summaries, which is basically a UDP broadcast of packets on your local network. So when I'm running this stuff, I'm running a mobile tether on my phone. So this is my internet hub, and on here it's broadcasting, and so that is broadcasting into my phone. And if I'm also running Chase Mapper either on my laptop, or actually I'm running Chase Mapper on that same Pi, the Pi is hearing those broadcast packets and it can receive the Chase Mapper data. So again, kind of nice when especially if you're getting this data more than once a minute, you can get a much smoother experience, better predictions, that sort of thing. So again, Chase Mapper integration, you would ask the question. Chase Mapper is actually software that predates SoundHub. But if you look at SoundHub, you're kind of looking at Chase Mapper. They have the same roots. But it's a local mapping interface. It runs on a computer in your car. I have it running on that Raspberry Pi right there. And I can open up Chase Mapper since this is my network hub. I can open Chase Mapper on my phone. I can open Chase Mapper on my laptop if I have it on this tether. Any device you want. I normally have a tablet mounted on my dashboard, and I have Chase Mapper on that tablet on the local network. So I have a nice big display of the map while I'm driving around, and my wife is yelling at me to look out for that cow, but we live in farm fields. So it runs in your car, can be accessed by a web browser. It gets live updates. Every packet that comes in, it's updating the map. It can download the GFS models, and it'll rerun predictions on the fly. And again, because I live out in hilly farm country, that's nice because I can't guarantee I'll have internet. About 50% of the time, I land somewhere where I don't have internet. And one or two unfortunate times, I selected a launch site where I didn't have internet, which really sucked. Because where I live in the Finger Lakes of New York, you don't pick a fixed location and go wherever it lands. You pick a landing location so it lands in the farm fields and not a lake or a forest, the state forest. Because it's either forests, lakes, or farms, and you want to hit the farms. So every launch is a different launch location, and I happened to pick one where it was a great location, landed right where I wanted to, but at launch time I had no internet, which is kind of annoying because I couldn't verify all my telemetry was working at the time. So yeah, these payload summary packets are broadcast, and Horus, the ModLive and Horus GUI both do that, so it automatically works with Chase Mapper. So why use Chase Mapper? Less internet dependency, as I said. I can't depend on pulling out my phone and getting to the internet when I'm recovering. It'll locally cache maps. It can locally cache the GFS model, so it'll even run predictions for you when you're off the internet, which is kind of nice. I always have to remember to mash the little button just before I launch saying, download the model, so I have them on my local computer. It's a natural fit with Horus to ModLive. Also, you can easily extend the use of those payload summaries. The payload summaries are in a standard format. It's a UDP broadcast of basically a JSON blob, if you're a geek. And that JSON blob is very predictable. So I've created scripts to make JSON blobs from data coming out of my D710. I hooked up a serial cable, plugged the serial cable into the Pi, and received the serial data out of my 710, turned it into a JSON blob, and put it on Chase Mapper. So I have a local APRS mapping into Chase Mapper. And also we do a lot of LoRa flights because we have students who like to use LoRa. And so I wrote a LoRa to payload summary gateway. And so again, those will just go on Chase Mapper. So I can use the same Chase interface no matter what protocol I'm using to track. All right, so that said, I mentioned that 8 script. Here was, until 20 minutes ago, our plan for tomorrow. I'm launching with Max and Seth and Oliver. We're sending up a big payload string. And so we're planning to have, and also Mark, who's got his air slicers. I don't think Mark is doing C and D. I think he's only doing A and B. But we had a free one. And Andrew over there got a free balloon this morning from the handout. And Andrew had a spare RS41 in his hand. So it's like, I got a balloon, I got a tracker, I got to do it. So as it happens, we have a free slice at 432/630. So when we get a break, I'm going to grab our programming dongle and reprogram his RS41, and we'll fly his balloon as well tomorrow. So that's our plan for using Horus for up to 8 payloads tomorrow. So, and with that, I'll knock my microphone off and then ask, does anybody have any questions? I know I want a mile a minute. I'm trying to keep us close to on time. Yeah.
So, totally not your main topic, but if you run APRS, your groups that use LoRa, do they run APRS packets over LoRa, or do they use some other?
Just their own, roll your own protocol. But at different times, we have done things like write a script to receive the LoRa and turn it into APRS and inject it into the APRS.fi stream. We've done that, and more recently I've done it with Chase Mapper and payload summaries, so a little of both. And uploading to SoundHub, obviously.
Might mention that CATS was added. to the-
Oh, yes, cats, I'm sorry, yes, cats. I am utterly and completely unfamiliar with cats.
Microphones for questions, sorry.
Oh, sorry. Yes, he commented that cats was added to RS41NG. I will be honest, I know nothing about cats, but it's another tracking protocol, and apparently getting some traction. So I got to keep up with the kids today and play with it myself. I just haven't yet, but it is in RS41NG. Anything else? Well, thank you for your attention.